First, before getting into the units and the measurements we have here for circles, let's actually try and understand what a circle is mathematically and in terms of geometry. So let's say that we have a point in space, like so. Obviously I gave it more dimension than a point really should have, like we talked about back at the beginning of the chapter, but let's say we have that point there, and we want to describe the set of all things of the same distance away from that point. So let's say that this measurement is the distance we're talking about. I don't have a string here, so it's not going to be perfect, but let's say I have that point like right there. If I spin this, I might end up with something over here and up here and swinging down and around, maybe out to here or somewhere up here, somewhere over there, and so many other points along that. Infinitely many points. Irrationally infinitely many points, for a term that you guys probably aren't very familiar with. But the point is, if I wanted to point all of these locations, what I would end up generating is a circle. And that's why, for those of you that have done a bit more with algebra, you may have seen the formula for representing a circle in space that looks a lot like the distance formula for measuring the amount of space between 2 points. And this is why, because circles are explicitly defined in terms of their distance from a central location, where we call this length out here from the center to any point along the circle. Though this obviously isn't a circle because my fingers aren't perfectly to scale and neither is my drawing ability. We call this the radius R, and I don't need those quotation marks there, that was a weird choice. But we call this the radius there, and if we take this idea and stretch it all the way across instead, I'm going to use that in a dotted line just for the differentiation, we call that the diameter, which we usually write with the letter D. And from there, we can talk about other things we do with circles. For example, the amount of space that the circle takes up on a plane, that is the area, as well as the length of the outside of the circle, something like the perimeter of the circle, which has a special name in this context we call the circumference, where the area of the circle is defined as the value here pi r squared, and the circumference is defined by 2 pi r, or pi times the diameter, and that's what this funky looking guy is there. If you don't remember it, that is the Greek letter lowercase pi that refers to a very specific, very important, and very long irrational number, 3.14159, and so on forever and ever and ever, because it never stops. Like I said, it's irrational, it goes on, and what it's specifically defined to do is help with this scenario, that pi was in a sense created, or maybe in a different way of thinking about it, discovered to describe the relationship between the radius of a circle and the circumference of a circle. That's why it's so important in the measuring scheme called radians. If you ever did anything with pre-calculus or trigonometry, it's why that pops up so much, because pi is specifically built for that purpose. And at this point, you've probably seen pi a few times, you have heard of pi at the very least, and we kind of treat it as a trivial given thing that pi just exists to fill this gap in knowledge, because taking away the rigidity of a polygon shouldn't take away the properties of a polygon in terms of perimeters and areas, but without those nice, rigid line segments to talk about, it's not quite as clean, and that's what we necessarily deal with when we're talking about circles. Where circles are, they're very important little shapes. You know, they've got their own great deal of
It's the circle of life.
Cultural value, as it were.
Someone once told me time is a flat circle. Everything we've ever done or will do, we're going to do over and over and over again.
Circles, as we can see, are very important, very necessary, very natural, very, in even some sense, beautiful shapes. And that very important value pi, as much as we do treat it as a thing that is just there, took a while to get to where it is now. That in antiquity, in ancient Egypt and Babylon, they had their own approximations for it in terms of fractions, things like 22/7, where the reason why we call it pi in particular comes from work by Greek mathematicians such as Archimedes and Apollonius of Perga and others, in terms of using a very special approach there by taking their circle and trying to fill it in with polygons of increasingly more and more shape until they got closer and closer to properly describing that circular region with a polygon. It's sort of an idea of a limit. It's sort of an idea for people who may have some interest in calculus of how we, in a modern sense, think of an integral. But that's way outside of the scope of this class. That's way beyond where we are in terms of complexity. The main thing I wanted to give us here is our two big formulas for circumference and area, and a little bit about where circles come from, why we might care about them, and where that funky looking value pi came from, because I'm sure it's a little controversial to you guys. It was even controversial in its own time, as it was said that the first mathematician to prove irrational numbers like this existed was drowned at sea because the Greeks couldn't accept that there weren't nice clean numbers for everything. So don't worry if this confuses you. This has confused people for its entire existence. It's always been a little controversial. Anyway, let's not go to quite those lengths. Let's just finish this section with an example for how this works computationally. So for this, we have the question, is a large pizza with a 16-inch diameter for $15 a better deal than a medium pizza with an 8-inch diameter for $7.50? So, for this, it's a bit of a problem-solving applied example here. Like I said, circles tend to be pretty natural shapes. They describe a lot of very well-known quantities, a lot of things that we and others might be particularly interested in. So, when we are dealing with these, well, we have to think in terms of our areas and circumferences, and in particular, we want to think here in terms of the price per square inch. So, we need the areas of each of our pizzas. So I'll say A1 for the 16-inch diameter and A2 for the 8-inch diameter, where for the 16-inch diameter, that means the radius in that case is going to be 8 inches, because r is always half of the diameter. So the area there would be pi times 8 inches squared, which we get as the value 64 pi square inches. And usually, we like to keep these things in terms of pi for as long as possible. In particular, if we don't want a decimal approximate, we're just trying to find a floating area, we actually like to keep it in this form because it's the most exact. You can't write pi in terms of a nice, even single decimal value. It goes on forever and ever, so we just keep it like this for now. When we get to the end, we will want an approximate because it's not entirely clear what 64 pi is just looking at it, but we don't want to worry about that just yet. Anyway, for our second one, we have roughly the same sort of idea. Pi times 4 inches squared, which in that case is going to end up being 16 pi square inches. So, if we want to get our prices per square inch, what we're going to do is take those sizes, those areas, and divide the price by those values. So, for the 64 pi square inch pizza, what we're going to do is take $15 and divide that by 64 pi square inches to get a value that is approximately 0.07 per square inch. That is 7 cents per square inch of pizza, which is a weird unit to deal with, but it is good for our comparison. And in the second case, we're going to take that value of 750 and divide it by 16 pi square inches and get that that will approximately be 15 cents per square inch. That's our cost in each of those cases. So the first one will cost about half as much in terms of the relative size, in terms of the price per square inch, which means the large pizza in this case is the better deal, which should make sense. That's a basic economies of scale thing for those of you that may have taken a macroeconomics class that if you make something cost more, you should get more, and it should cost less in terms of the marginal amount there, in terms of the amount per whatever unit you might want, because they're giving you more, you have to pay more, they have to make it a better deal, otherwise no one would take the bigger one, they'd just take a bunch of small ones. Anyway, that's our main set of ideas for working within 2 dimensions. So, we're going to move on to section 10.5 to look at things in terms of our 3-dimensional shapes. See you in there.